So sections 9.1 through 9.3, we're talking about two sample tests. So we just figured out how to test for one sample for mean. Now we're going to do it for two samples. Okay. So sometimes we want to compare two different populations. Okay. Looking at these box plots for different sets of two populations, what are some things you might want to try and compare? Things we learned about in Chapter 6. I think we might want to compare means, standard deviations. What other things can we compare? Mean, standard deviations. We could also compare like medians, range, etc. Basically, any statistic you can think of, you could probably compare. Specifically, we talked about our two main things we might want to look at are center and spread. Now, looking at a box plot, you can't see means and standard deviations on a box plot. Okay, at least not very easily on most box plots. Okay, so we might want to compare center, and on a box plot, it's easy to compare the medians, okay, because they always put a line at the median, so that's why it's easy to compare the medians. And you might want to compare spread, which on a box plot, we're going to do our interquartile range. Remember what that is. So the interquartile range is just the difference between third and first quartile. The reason it's easy to look at that on a box plot is your box is goes from your first to third quartile. So the box length is your interquartile range. Now, that's not the only way to compare center and spread. Usually we look at the mean and standard deviation, but that's hard to do on a box plot. So as far as the box plots go, we're going to look at the medians and the interquartile range. So when you look at these first two box plots, okay, how do their centers compare?
Same.
Okay, so the centers are the same. Okay, what about the spread or the interquartile range? Okay, so the bottom one has much smaller spread. So it has a smaller interquartile range, it has a smaller standard deviation. Even though I can't tell exactly what the standard deviation is, I can tell that it would be smaller. What about the next set?
The centers are different, but the spread looks about the same.
So center is different, but the spread looks to be about the same. And remember, that was one of the reasons that we first said, okay, we need to look at the spread, is when we had 2 data sets that had the exact same means and medians, but looked very different. It was the spread that was different. Okay. So this next one, it looks like the top one has a higher center. And higher spread. And what else does the top one have?
An outlier.
And a potential outlier. let's see, what about the last one? The top one has a higher center. What about its spread? Looks like slightly smaller spread. Now, we haven't talked about range very much in this class either. Do you remember, range is the difference between the maximum and the minimum. So their ranges look like their ranges could actually be pretty close, but the interquartile range is smaller on the top. And because, so my mean would be somewhere in here, because your mean, or you have more values close to your mean, your standard deviation would also be a little bit smaller. So you can judge the standard deviation a lot better by the interquartile range than you can by the overall range. So this is how you might want to compare two populations. There are ways to compare center, which we'll do mathematically with our means, and there are also ways you could compare the standard deviations between two populations, which we probably won't get to in this class, but if we have extra time we might throw that in, because it's kind of fun too. So why do we want to compare two populations? Really, in practice, you're going to be more interested in looking at two populations usually than you would be in just one population. So two populations could be people on experimental treatment A and people on experimental treatment B. Or more often, it's people on experimental treatment and people on a placebo. Okay? Or one population is your old process and one population is your new process. Okay, and when you compare these two populations, you can see which treatment or process gives better results. And so to do this, we'll take samples from each population. There's different ways we can take samples. The first one we're going to talk about is paired samples. So for example 1, we want to compare the repair costs of moderately damaged cars at two garages. So basically, we want to see if garage 1 charges customers more to repair their cars than garage 2. Okay. So there's different ways I could do this. First of all, if I took independent samples. So independent samples, remember, anytime it's independent, that means like they don't affect each other somehow. So we could take, say, 10 cars to garage 1 and get cost estimates for the repairs. And then we could take, say, 15 cars to garage 2 and get estimates there. Notice when we do this, we don't have to have equal sample sizes. It's common to have equal sample sizes, but not required. Okay, so we take some cars to garage 1, some cars to garage 2, and get repair costs at each one. But what if, even though I randomly selected them, what if the cars that I took to garage 1 just happen to be more expensive than the cars that I took to garage 2? Then the repair costs are going to be higher, even though garage 1 might not really charge more than garage 2. Okay, so we need to find a method that might work better. So what we're going to do is you could do some kind of paired samples, or other books call it matched pairs. So what you could do is take 10 randomly damaged cars and take them to both garages and get estimates at both places. Then you'd completely eliminate that source of bias because each garage would see the exact same car, and so you could really see if the differences were due to which garage and not just which car you took to which garage. So for another example, like what if we wanted to compare two brands of tires to see which one lasts longer? So if we use independent samples, we could put brand A on 30 cars and brand B on 30 cars. But what could be the problem here? What are some possible sources of bias that might crop up?
Different drivers, driving styles.
Different driving styles. What else could be different? Maybe the train, the mileage, etc. So what if everyone on brand A just happens to drive from North Logan to Logan every day, and everyone on brand B happens to go to St. George and go off-roading or something? Okay, are you going to see a difference in which brand lasts longer? Yes. So when we take independent samples, we hope to eliminate a lot of that bias by saying, okay, because we're randomly choosing people, hopefully half the people in Logan go in each group and half the people in St. George go in half each group. So you kind of hope that happens, but you can't necessarily guarantee it. So we prefer to do these matched pairs, or paired samples, which if it's not independent, we could call it dependent. So how could you do paired samples for this situation where you could get rid of the different driving styles, terrain, mileage, etc.? Not necessarily the right way, but how could you do this?
Could you put both types of tires on one car?
So both types of tires on each car. And that way, each brand will have the same driving style, the same mileage, and everything else. So you get rid of all of those possible sources of bias. And in any study, your goal is to get rid of as many possible sources of bias as you reasonably can so that your results will be more accurate and more trustworthy. So what if we wanted to test 2 new drugs on patients? So if we did independent samples, we could test, say, like 40 patients on drug A, 50 patients on drug B, and compare the results. Okay. And even though when we do independent samples, we're hoping to get rid of bias and have both samples be fairly equivalent, if I'm just choosing random samples, I can't guarantee that. So maybe all the patients on drug A would happen to be older, so they don't respond to it as well. Or maybe everyone on drug B just happens to exercise more, so they seem to work better. Okay. So we might not want independent samples, but if we try to do, like our last example, and put both types of, instead of both types of tires on each car, what if we try to give every person both types of drugs? What could happen there? Medically speaking, what would happen if you gave each person both types of drugs?
Well, you wouldn't know which one's doing what, but they also could cause bad side effects by mixing.
Yeah, we wouldn't know which one's doing what, and we could cause interactions between the drugs, which could give you really bad side effects. Okay. So what are some things that you could think of to try here? Okay. Be a little creative.
Someone you could start using like placebo.
We could do placebos and then the drug, but that would give us still kind of more right independent samples if you just put people in both groups. Like, how could you try and go to a matched pairs? Somehow we need to have paired samples, or at least kind of close to matched pairs.
Well, do you have to pick the people randomly? Because if you didn't, you could get 2 people that are kind of in a similar situation with the same age, and then put one on one brother and one on the other.
So that's usually what we're going to try and do, is we try to match people up. By height, weight, health, we could do like gender, age, etc. So you try and match them up as best as you can, and depending on how much time and resources and people you have, you might be able to match them up by all of these, and race, and religion, and all of these different things, or you might just be lucky if you can get gender and approximate weight, or something, okay? But so you match them up as best as you possibly can, and then randomly assign one from each pair to each drug. So you match up the pairs in advance and then randomly assign one to each drug. And that will give you not exact pair samples, but pretty close. And so you could get rid of just a little more bias that way. So any questions here on the setup? Okay. Now again, this is probably like our best golden ideal, like if we had all the money in the world, we'd always do paired samples because you'd get the best results. Lots of times you can't do in practice, and we will do independent samples, but if you could, paired samples would be the best. So let's say we want to do a hypothesis test for our paired samples. Okay. So the repair costs for 2 different garages are listed below. They're in hundreds of dollars. Okay. So here are 7 cars. We have repair costs at garage 1, repair costs of garage 2. What we're going to do where these people are paired up is it makes sense to find the difference for each pair. Okay. So like 7.1 minus 7.9 would give me negative 0.8. Okay. And the reason I'm doing garage 1 minus garage 2 is just because garage 1 happened to be on the left, and that seemed more intuitive. I could have done garage 2 minus garage 1. I've just then all of my things would change like signs throughout the rest of the test. Okay, so for car 2, we need 9 minus 10.1 gives me negative 1.1. 11 minus 12.2 gives me negative 1.2. Let's see, positive 0.1, 0.5, 0.7, and 1.4. Correct me if I'm wrong.
Need to be negative, right?
Yes. Negative 0.5, negative 0.7, negative 1.4. Okay. So what we do, because they are paired samples, it makes sense to us to find the difference for each pair. Now that I've done that, notice I have just one data set for one sample. And with that data set, I could look at the box plot. Okay. I could look at the normal quantile plot, and I could find my descriptive statistics. Okay. So for my paired differences, I have my counts. That told me there were 7 of them. If I want, because they are differences, I could put little D's on everything to remind myself that they are differences. You don't have to, but if you want to remind yourself. The mean, so that's the average for the differences, is negative 0.8. And the sample standard deviation of the differences is 0.503. So what happens here is we wanted to know if garage 1 charges less than garage 2. Okay, so we want to know if there's a difference in the true population means. Okay, so we looked at our paired samples and we found the difference for each pair. So at this moment we really only have 1 sample, and so we don't actually need a new test because you already know how to do a test for 1 sample. Okay, so in this situation, would you want to do a 1 sample z-test or a 1 sample t-test? T-test, because we know S instead of sigma. Okay, so really we're just going to use 1 sample t-test, so it would just be x bar minus my hypothesized mean of the differences over the standard deviation over square root of the sample size. Okay, but I wrote here, usually it's just going to be this formula. Okay, so why do you think it might be that formula? So here's why. Okay, so we want to know is the mean for garage 1 less than the mean for garage 2? That's really the question that we're asking here. Is the mean for garage 1 less than the mean for garage 2? So if we look at those two means, okay, then the null hypothesis would be that mu for garage 1 equals the mean for garage 2. Okay. Now, if those two population means are different, okay, then what would you expect for the mean of the differences? Okay, so if your two population means are equal and you went through and you found the differences for all your possible pairs, what would you expect that mean of for the differences to be?
0.
0. Okay. So if your two means are equal, then we would expect the mean for the differences to be equal to 0. That's kind of what we'd expect. So what happens here is when we say our hypothesized mean for the differences, that's usually just going to be 0. And so it's just minus 0 every time, which of course you don't need to bother writing down in a formula. So that's why it usually looks like this. But really it's just a one sample t-test. So for a one sample t-test, let's go through and follow our normal steps. Okay. We need to pick a significance level. If they don't tell me 1, then let's choose alpha equals 0. Okay. No, that doesn't make sense, does it? Got a little distracted there. How about let's try alpha equals 0.05. Let's see, we also need to check our assumptions. Do you remember what our assumptions are? Okay, we need a normal population or a sample size of at least 30. So are one of those met here? Okay, get that normal quantile plot. That looks fairly like a straight line. So we have fairly normal. And then we go with our null and alternative hypotheses, which is usually our mean equals or mu is less than, mu is greater than, etc. Since we're talking about the differences, let's just put a little mu d here. If the null hypothesis would be that the two groups are equal, we'd expect that the differences, the mean of the differences should be 0. So for your paired sample test, this is always just going to be that the mean of the differences is 0. Then the hard part comes in which direction should you put your alternative hypothesis. Okay. So we wanted to know if garage 1 is cheaper than garage 2. I didn't say it at the top, so let me just write it down. So is garage 1 cheaper than garage 2? So that was the question we wanted. So if we do garage 1 minus garage 2, so if garage 1 is cheaper, so we're going to have small values minus big values, which should give me overall negative numbers. Okay. So it's garage 1 cheaper, so I should have small minus big, so that should give me negative numbers. So do I want my mean of my differences to be less than 0 or greater than 0? Less than 0. So that's the hardest part, is just trying to figure out which way that sign should go. What comes next in our hypothesis test? Our test statistic, t. So it's x bar minus my hypothesized mean over s over the square root of n. And remember, because this is differences, I could, if I wanted to, put little d's everywhere I want. Okay, so look up above at the page. What was the mean for our samples? Negative 0.8 minus my hypothesized mean of the differences, which is 0. The standard deviation was 503, and the square of the sample size, which I remember right, is 7. So we have negative 6.01. No. If you type it in your calculator correctly, you should get negative 4.207. Anyone else? Okay. What else do you need for a t-test? Degrees of freedom, which are, do you remember, n minus 1, so 7 minus 1 is 6. And my p-value p-value, we're at negative 4.207, and which direction did I want to shade? To the left, because I want to know if the mean of the differences was less than 0. Okay, so we need to go to the t-table. We have 6 degrees of freedom. And we're looking for 4.207. Remember, we're going to use our symmetry here, which would put it about here. So my p-value is between 0.005 and 0.001. Compared to our level of significance alpha, is that a big or small p-value? That's a small p-value, so we will reject the null hypothesis. And if we reject the null hypothesis, really that means we have, so it's evidence that the mean of the differences is less than 0. So that's really what we found. Let's now state it a little more in the context. So, evidence that the mean cost at garage 1 is less than the mean cost at garage 2.
Can you explain one more time why we didn't use less than 0 for the alternative hypothesis?
So I don't remember for sure what I put on the previous page, because I made up the example and then I made up the data. But for here, let's say we want to know if garage 1 is cheaper than garage 2. Okay. Now, when we found these differences, I started doing garage 1 minus garage 2, just because that was what seemed easier to me, to do garage 1 minus garage 2. So if garage 1 is cheaper than garage 2, then this should be small minus big values, correct? And so if you have small minus big values, are you going to get negative or positive values? We will get negative values. So we're looking for the mean of the differences would be less than 0.
So if you happen to choose garage 2 minus garage 1, it would be the opposite.
Then it would be the opposite. But if we'd chosen it that way, then instead of my mean being negative 0.8, my mean would have been positive 0.8, and we would have been looking for that in the right tail, and all of our results would have ended up being the same if I did everything correctly from there. Okay. So other questions on this. Okay, the biggest new thing is trying to figure out which way should my sign go. Because the rest of it is just the one sample t-test, which you know how to do. According to our test, you know how to do it pretty well. So for our next example, just to practice setting it up some more, some people think that mental patients are influenced by the moon. We conducted a study of dementia patients in nursing homes. For each patient, we counted the average number of disruptive behaviors on days with a full moon, and also the average number of disruptive behaviors on days without a full moon. And because you're doing this for each patient, then it is a paired sample. Conduct a hypothesis test to determine if there are more disruptive behaviors on days with a full moon. So we want to know, is the mean for the moon, let's see, greater than or less than mean for other? Greater than. So that's what we're looking for. Okay. Now look at the difference. So I did give you a table here. So which way did they subtract it? Let's see, so it must have been moon minus others. So when I look for the mean of the differences, okay, we want to know if that's greater than or less than 0. It should be greater than, because if the mean for the moon is bigger, then we should have big numbers minus small numbers, so it should be greater than 0. Let's see, let's write down the summary information they gave me too. So the count, that is my sample size, so that's 15. My mean, x bar for the differences, is 2.4327, and the sample standard deviation, again for my differences, is 1.4603. So any questions on our setup? So we just go through everything like normal. Okay, pick a significance level just to mix it up so that you can do different levels. Let's try 0.01. And then for our assumptions, we need it to be normal or n at least 30. Okay, are one of those met? And if so, which one? It looks fairly normal. We do have a little issue right there, but overall it seems like a mostly straight line, so I'm going to feel okay going with the normal part of it. See, my null hypothesis would be that my two means are equal, so that the mean of the differences is 0. And my alternative, based on what we wrote up above, we want the mean of the differences to be greater than 0. Next step, find the test statistic. Which is the same formula, I just put on D's to make it seem fancier. So 2.4327 minus my hypothesized mean the differences, which is 0, over 1.4603 over the square root of 15. And let's see if I can print my calculator correctly this time. .4519. What else do I need for my t-test? I need degrees of freedom. So 15 minus 1 gives me 14. So for my p-value, here's my 6.4519. Am I looking for the area to the right or left? To the right? Because my alternative hypothesis is greater than. Remember that sometimes based on your alternative hypothesis, you might actually end up shading the big area. It doesn't happen very often, but it could happen. So just keep that in mind and don't get in the habit of just picking the smaller tail. So 14 degrees of freedom. I'm looking for 6 point something, which would be off the chart. So my p-value is less than 0.0005. So smaller, bigger, small p-value. And do I need to reject or fail to reject my null hypothesis? So I heard someone say reject. So small p-value. So I will reject my null hypothesis. And so what have we shown here? We showed that mu d is greater than 0. So in context of my problem, coming back up, if the mean of the differences is greater than 0, that means the mean for the moon is greater than the mean for the other days. So we found extremely strong evidence that the average for all mental patients is higher on moon days. You've seen it?
My wife worked in an Alzheimer's ward ago, and that's how
It's just crazy. Does she know why?
The same thing in hospitals. Will always come in on full moons.
Yeah, I've heard that. Like the emergency room is really busy. And so we know it's statistically significant. So we just showed that we had extremely strong evidence. And if you want to look at practically significant as well, I mean, our mean is 2.4. So these mental patients are having an average of like 2.4 more episodes on moon days, which seems to me like a fair amount. So that's probably practically significant as well. When, the high is 3 or 4, so being 2.5 higher seems like quite a big deal. Okay, so any questions on our hypothesis test? Now, if we can do hypothesis tests, we probably also want to find confidence intervals. And just like doing our test, we did the exact same thing as the t-test. We're going to use our exact same formula that we did before with our t confidence interval, but we'll put little d's on it to remind ourselves that it is for the difference. Okay, so that's our confidence interval, and remember we have n minus 1 degrees of freedom. Okay, so for example 6, find a 95% confidence interval for the mean of the population differences. Okay, so this is the same as asking for the difference between the two population means for the repair cost. So I could word it either way. So the mean of the population differences will be equal to the difference between the two population means. It's one of those nice things that works out. So remember on this one we did do garage 1 minus garage 2. Which we know because we worked over this problem previously. So garage 1 minus garage 2. Notice it gives me my count, my mean, my sample standard deviation. All we really need to do is plug it into that formula. What do I need before I can plug everything in? A critical point. So if I want a 95%, then how much area goes in each tail? We need 0.025, right? And my degrees of freedom are n minus 1, so in this case, 6. Okay, so go back to your t-table. 6 degrees of freedom, we're looking for an area of 0.025 in the tail, which would put me at 2.447 is my critical point. So let's just plug everything into our formula. And of course, if I have T star anywhere, that's just my shortcut notation of saying T with alpha over 2 area in the right tail and n minus 1 degrees of freedom. It's just a little bit shorter. So my mean for my differences was negative 0.8 plus or minus my critical point of 2.447 times standard deviation 0.503 over the square root of sample size, which was 7. Again, exact same formula we've used before. All that we've done is just remember we're doing it for differences. Now, these numbers probably should have been in like thousands of dollars or something, but I don't think I ever said, did I?
You said hundreds of dollars.
Did I say hundreds?
Yeah.
Okay. Okay. So that's my confidence interval, but what does it really mean? Okay. So I could say something like, I am 95% confident that the mean for all of the differences will be between negative 1.26 and negative 0.33. That's not really that informative for my boss. Okay, so let's come back. Okay, so we had garage 1 minus garage 2. So if we're getting negative numbers, which one of these garages charged more?
Garage 2.
Garage 2 must have charged more because it must have had higher value. So because I got these negative numbers, it must have been that garage 1 was small, garage 2 was bigger. So I could say something like, I am 95% confident that garage 1 charges an average of, or an average between, let's see, negative 1, or well, we don't need to put in the negative, we can just say it just charges between $126 and $33 less than garage 2 for on all cars. Okay, so on average, we're sure that, or 95% confident the garage 1 charges somewhere between $126 and $33 less than garage 2. Okay. Or however you want to reword that, but looking at it, we knew that garage 1 was less, and so you just need to throw in that word somehow, the average of the populations. Again, the biggest thing is just how you're interpreting it, making sure you do it right with your paired differences. So for example 7, find a 95% confidence interval for the mean difference in aggressive behaviors per day. Okay, so the mean difference between moon days and other days. Remember, we did moon minus other. And why is it important to know which direction I subtracted them?
So you can know which direction to go.
So I know which direction to look for, and I know, like, if I get positives or negatives, I know which one ended up being higher. So again, for a 95% confidence interval, that would leave me with 0.025 in each tail. My degrees of freedom are n minus 1, so 14. Let's go find our critical value. Of 2.145. So T star equals 2.145. And we just have to plug everything in. So the mean, 2.4327, plus or minus our 2.145 times my sample standard deviation over the square root of the sample size. So I got from 1.6 to 3.2. I know this. Okay. If I say something like, I am 95% confident that the average for moon days is between 1.6 and 3.2. Now, is that higher or lower on the moon days? And how can you tell?
Higher.
Because we did moon minus other and we got positive values, so moon must have been greater. So the average for the moon days is between 1.6 and 3.2, higher than the average for other days. So we still don't know for sure what my population mean is, but for my test, I was sure that the mean of the differences was greater than 0. And now I can say, well, not only am I confident that it's higher, but I'm confident that it's between 1.6 and 3.2 higher. So really, which one gives you more information, a hypothesis test or a confidence interval? Confidence interval. Hypothesis test just says greater than 0 or not, but confidence interval says, well, I'm actually 95% confident it's between 1.6 and 3.2. Okay, so last chance. Any questions there? Take your 2-minute break.